Hello, in this video we're going to be looking at implicit differentiation using MATLAB. So in the video I will show you how to implicitly solve example 3, dy dx, find dy dx if y squared equals x squared plus sine of xy. And then we're also going to look at higher order, example 4, it's d squared y over dx squared if 2x cubed minus 3y squared equals 8. And then in the last example, I will show you example 2 of this book. So we're going to find the slope of the circle, x squared plus y squared equals 25 at the point 3, negative 4. And we're going to also graph this example and get a graph like this on the figure 3.31. All right, so let's jump over to MATLAB. I've put all the examples in there and commented what they are. Example 3, example 4, and example 2. So that's the order we will be going by. All right, so let's go ahead and start. All right, so this is how we do implicit differentiation. There are several other ways to do it also, but in this video I will show you this way. And let's go ahead and uncomment this first example and see what we get. When I run the code, I get that. Well, let's go ahead and put semicolons. So we just want to see what dy dx is. So dy dx is we get 2x plus y cosine of xy over 2y minus x cosine of xy. And let's see if that's what the book gets also. So let's go back to example 3. Their answer is this. It's the same as what we got. Okay, and if I go back to my code, I did this last step subbing this y for the y here. I did this because if I comment this and run it, I get things in terms of y of x. So y is in terms of y of x. If you notice, see, this is a different answer because y depends on x. And this is a little bit uglier. That's why I did a last step here to show you exactly what the book gets. See, if I run it here, I don't have that y of x in there anymore. So it's y, not y of x. Okay, so if we wanted to do, let me show you dx dy really quick also. So let's go ahead and comment this. So if you want to do dx dy, all we have to do is we say dx dy equals 1 over dy dx. It's just a reciprocal of this last code. So if we run this, we should get the reciprocal of each other. So dx dy is 2y minus x cosine xy over 2x plus y cosine xy. So this is, let's go ahead and do some comments. So this is first order dx dy, and this is first order dy dx. All right. Next, let's go ahead and do second orders. So we're gonna look at example 4, and we're gonna see if we get the same answer as what the book gets. To do that, though, we need to comment this last one because I will show you why in a minute. Because we need to have y of x when we convert when we're looking at d squared y dx squared. It's important not to have that substituted because we need the independent variable and dependent variables. All right, let's go ahead and do that. All right, let's see what we're going to get. First of all, let me explain. So I created a temp variable to store dy dx, and we're going to differentiate dy dx with respect to x, and then I simplify and substitute into the temp dy dx, and then we substitute y into, when we have y of x as the independent variable, to make it look prettier, and then lastly we collect terms. This will simplify things for us to make it look like the book. All right, so let's go ahead and uncomment. So comment this example and look at example 4. Sorry, so I uncommented the wrong code. So I'm supposed to uncomment example 4. F equals 2x cubed minus 3y squared equals 8. And when I remove that semicolon and run it, we get minus 1 over y cubed x to the 4th plus 2 over y times x. And this is what the book also gets, 2x over y minus x to the 4th y cubed. All right, so let's jump back over to our code. Let's comment this and solve the last example. So we're gonna solve example 2 now. Example 2. So let's uncomment that and comment this, and we're gonna start adding to this code here and see what we get. All right, so all I did was I find the slope. Slope is dy dx evaluated at x1 and y1. x1 is 3 and y1 is -4. And then what I did after that is I created a new variable. This is the equation of a line. So I called the line equals m is what we found, and times x minus x1 plus y1. So this is the point slope form of a line. So if we run this, see what we get. So the equation of our line is 3x over 4 minus 25 fourths. All right, and let's see if the book did get that. They don't have the equation of a line here in the book. If I go to example 2, they get the slope is 3/4. So they only solve for the slope, and that's what we got. So if I put a colon here and run it again, we should get 3/4. M is 3/4. Good. All right, so now I'm going to solve. Well, we're gonna graph this example here. All right, so I'm gonna start graphing. All right, so I put in my graph code for my graph, and I also put it up here in terms of m and the line that we want to graph, and we have to also comment out the code that we found for dy dx. So when I run it here, I get the graph of both the circle and the line. Let me pull it out and make it bigger. So we have the circle plotted and the tangent line at the point 3, 4. It looks like the circle has the center at 0, 0 and a radius of 5. And I also have a legend to show the curve and the slope. All right, so this is how we do implicit differentiation in MATLAB. Thanks for watching.